Good morning, dear students. So we started with atomic models. Okay, Thomson model we discussed, Rutherford model we discussed. Okay, now before starting with Bohr's atomic model, okay, there are few topics that we have to discuss. The first is atomic number. Okay, the first concept is atomic number. What is the meaning of atomic number? Atomic number is always equal to the number of protons, and number of protons are present in the nucleus of the atom. If your atom is neutral atom means it does not have any positive or negative charge, atomic number is equal to number of protons, that is equal to number of electrons, because for neutral atom protons and electrons are always equal, and this atomic number is symbolized as Z. Now mass number is symbolized as A, and it is equal to number of protons plus number of neutrons. Okay, now suppose this X is my element, so Z is written here and A is written here. Okay, so this is atomic number and this is mass number. I have taken one example, 7 and 14. So 7 is the atomic number, 14 is the mass number. If atomic number is 7, how many protons are there? 7. And since this is neutral, so electrons will also be 7. Now mass number is 14. Now how to find out number of neutrons? So number of neutrons are mass number minus atomic number, that is number of neutrons will come 7. Okay. Now next is the concept of isotopes, isobars and isotones. Okay, so first we'll discuss what are isotopes. Isotopes are those atoms belonging to the same element which have same atomic number, okay, but different mass number. These things you know, we are just revising the things. Now what are the examples of isotopes? So 1H1, 1H2 and 1H3. Okay, this is hydrogen, this is deuterium, this is tritium. Atomic numbers are same but mass numbers are different. Now carbon, atomic numbers are 6, 6 and 6 and mass numbers are 12, 13 and 14. What are isobars? Isobars are the atoms of different elements having same mass number but different atomic number. So examples I have taken. Now this is argon, this is potassium, this is calcium. Atomic numbers are 18, 19 and 20. Since the atomic numbers are different, so element is also different but mass numbers are same. Now isotones. Isotones have same number of neutrons. Okay, now examples I have taken. Now this is carbon, this is nitrogen, this is oxygen. So number of protons are 6, 7 and 8, that is atomic number. Mass number is also different, 14, 15 and 16. But if you subtract these two, your neutrons will come 8. So all these have total 8 neutrons. Okay, now one question is there for you. You can easily do this. We have to complete the following table. So mass number, atomic number, protons, neutrons and electrons. Okay, these 5 columns are there and the elements are oxygen, aluminium, this is Cl minus, okay, one negative charge is there, and Mg2 plus positive charge is there. And what happens because of this negative and positive charge? No effect on number of protons and neutrons. If negative or positive charge is there, the effect is there only on the number of electrons. If negative charge is there, electron is extra, we have to add electron. If positive charge is there, it means we have to subtract electron. Okay, so you will complete this table. Okay, now let's move on to the next topic, that is drawbacks of Rutherford model. Okay, why Rutherford model failed? Okay, now the first failure was it did not explain the distribution of electrons around the nucleus and their energies. Okay, now if more than one electrons are there in the atom, how these electrons are distributed and what are their energies? Okay, so it failed to explain that thing. Now the second drawback, that is the most important drawback, was according to Maxwell, whenever a charged particle moves under the influence of attractive forces, it continuously loses energy in the form of radiation. Clear? Now electron is also a charged particle and electron is revolving around positive nucleus, negative, positive attraction is there. So electron is a charged particle, it is continuously moving around nucleus which is positive, so definitely there is attraction between the two. So it means that electron should continuously lose energy at every turn. So after every revolution, electron should lose energy. And if electron is losing its energy after every turn, what will happen? Its energy, its velocity will decrease. Clear? And what will happen? It will move closer and closer to the nucleus. Because its orbit will become smaller, the energy, electron is losing its energy, its velocity is decreasing, so its path will become smaller and smaller, and ultimately what will happen? It should fall into the nucleus. This should happen actually if electron is negative and nucleus is positive, and electron is continuously revolving around the nucleus. But it does not happen. Atom is quite stable. Okay, so Rutherford failed to explain the stability of the atom. Okay, so he was not able to explain that why this does not happen. If Rutherford is correct, this should happen. This is negative electron, this is positive nucleus. Electron should fall into nucleus. Atom should collapse. But this does not happen, and Rutherford was not able to explain this entire thing. Clear? So this was the second drawback of Rutherford model. Now, developments leading to the Bohr's atomic model. Okay, now the next model of atom was Bohr's atomic model. Now, between Rutherford model and Bohr model, several developments were going on. So before starting with the Bohr's atomic model, we have to understand those developments which contributed lot in explaining the drawbacks of Rutherford model, and which contributed lot in the improvement of Bohr's atomic model. So first we'll understand those developments, and afterwards we'll take Bohr's atomic model. The two developments were, first, dual nature of electromagnetic radiation, and the second development was atomic spectra. So one by one we'll take these two topics and we'll understand them. Now let's discuss the first development towards Bohr's atomic model, that is nature of electromagnetic radiation. Okay, now first we'll discuss what is the meaning of electromagnetic radiation. Okay, now it was proposed that light has dual nature. Dual nature means it has wave nature as well as particle nature. Okay, and first we'll discuss the wave nature of light. Okay, so first we'll understand little things about light, and then we'll apply the same thing on the atom. Okay, so first we are going to discuss the nature of light. So Maxwell said that light and other forms of radiant energy. Now what is the meaning of this? Radiations emitted from any light source, whether it is sun, whether it is tube light, whether it is bulb, or the radiations emitted from any hot object, they always travel in the form of waves. This is wave theory. This is Maxwell's wave theory, that radiations always travel in the form of waves. Waves means continuous motion is there. Okay, as soon as you switch on your light, the waves, it will start emitting waves, and that will continuously reach to you. Okay, now these waves have both electric field and magnetic field associated with them. That's why these are known as electromagnetic waves or electromagnetic radiations. So whatever radiations are emitted from light source, or whatever radiations are emitted from any hot object, these radiations are known as electromagnetic radiations or electromagnetic waves. They have wave nature. They travel continuously. Clear? They have continuous motion. Now what are the characteristics of these electromagnetic waves or radiations? The first is, these do not require any medium for propagation. Medium means they can travel in vacuum also. Okay, for example, the sunlight is reaching to us after passing through space, and that is having no air, that is vacuum is there. Okay, the second is, these radiations travel with same speed, that is 3 into 10 to the power 8 meter per second. And what this speed is? This is the speed of light. So all electromagnetic radiations travel with the same velocity or speed. These have both electric field and magnetic field perpendicular to each other, and also to the direction of propagation of wave. Now what is the meaning of this third characteristic? Suppose this is the direction of wave, and in this direction the wave is propagating. Now the wave is having electric field and magnetic field. So this dotted line indicates electrical field component, and this solid line indicates magnetic field component. Both the components are perpendicular to each other, and also to the direction of propagation of waves. So these are the three important characteristics of electromagnetic waves or radiations. So what is according to Maxwell's wave theory? So Maxwell's wave theory says that all radiations, okay, travel in the form of waves. They travel continuously in the form of waves. Now if we want to understand this wave theory, first we have to understand what are the important characteristics of waves. Now this is wave motion. Wave travels like this. This is crust, this is trough, this is crust, this is trough, like this. Okay, continuous motion is there without any interruption. The first characteristic of wave is wavelength. Wavelength is denoted by the symbol lambda. Okay, and what is this wavelength? It is the distance between two adjacent crust or adjacent troughs. So from here to here it is wavelength, from here to here it is wavelength. Wavelength is generally expressed in terms of angstroms. Okay, angstrom is A naught. Okay, it is generally expressed in angstroms, and 1 angstrom is 10 to the power minus 10 meters. We can also express this wavelength in terms of nanometer, picometer, micrometer. Okay, so in small units of distance the wavelength is expressed. The second characteristic of wave is frequency. Frequency is symbolized as nu. Okay, this is the symbol for nu. Okay, and what is the meaning of frequency? Number of waves passing through a point in 1 second. Okay, and what is the unit of frequency? It is hertz. And what is 1 hertz? 1 hertz is 1 second inverse. Okay, so this is the meaning of frequency. Now the third characteristic of wave is amplitude. Amplitude is denoted by the symbol A. And what is amplitude? It is the height of crust or depth of trough. So this is my amplitude. This is A, this is A. Okay. And what is the fourth characteristic? It is wave number. Wave number is denoted by nu bar. Okay. And it is equal to the inverse of wavelength. That is reciprocal of wavelength is wave number. So nu bar, it is denoted by nu bar. It is 1 upon lambda. And the last characteristic of wave is velocity. Velocity is symbolized as c. And since all electromagnetic radiations travel with the speed of light, so we'll symbolize it as c. And what is velocity? Distance traveled by wave in 1 second. And what is the unit of velocity? Meter per second. So these are the important characteristics of your waves: wavelength, frequency, amplitude, wave number, and velocity. Now there is one relation between wavelength, frequency, and velocity. And what is that relation? There is one formula: c is equal to nu into lambda. C is the velocity of light, nu is the frequency, and lambda is the wavelength. So since we know the value of c, that is 3 into 10 to the power minus 8 meters, c is the constant value. So it is always equal to nu into lambda. So we can write like this. C is constant, so we can write nu is frequency is inversely related to wavelength. Okay, suppose the electromagnetic radiation has large frequency, its wavelength will be less, or vice versa. So this is the formula which is showing the relation between the three quantities: wavelength, frequency, and velocity. Now the next is electromagnetic spectrum. Okay, now what is the meaning of electromagnetic spectrum? We have learned that when sunlight is passed through prism, it splits into 7 colors. Okay, violet, indigo, blue, green, yellow, orange, and red. And all these colors have different wavelengths and different frequencies. Is this clear? But sunlight not only contains the 7 colors or the visible region. The sunlight also contains UV rays, IR rays, microwaves, radio waves. Okay, and we can see only the visible region, because our eyes are capable to see only the visible colors which are present in visible light. We cannot see ultraviolet radiations, X-rays, or microwaves through our naked eyes. Okay, but sunlight also has all these radiations. Okay, so this is electromagnetic spectrum only. So what is electromagnetic spectrum? The arrangement of different types of electromagnetic radiations in the order of increasing wavelength. And since the wavelength is increasing, we can say the frequency is decreasing. Now, how many types of radiations are there in the electromagnetic spectrum? First is gamma rays, X-rays, UV, ultraviolet. Now this is my visible region. Visible region is again divided into 7 colors: Vibgyor, IR, microwaves, radio waves, long radio waves. Okay, now you can see this is frequency. So 10 to the power 24 to 10 to the power 0, frequency is continuously decreasing. And this is wavelength, 10 to the power minus 16 to 10 to the power 8, wavelength is continuously increasing. Okay, here wavelength is expressed in nanometer. What is nanometer? 10 to the power minus 9 meter. Is this clear? So the arrangement of different types of electromagnetic radiations is known as electromagnetic spectrum. Is this clear?